Okay, so today, as I mentioned, we're going to work on counting experiments. So this is another way that data will come out because a lot of science ends up figuring out whether or not, something exists or not. So like, whether or not. So in this little example here, is a this is not a plot as you remember them what we did last time. These are actually what's known as a histogram. So you can kind of tell when things are histogram when they are especially in these like bar graphs. Sometimes they're called bar graphs. That's what I remember when I was a kid. But these are not bar graphs, even though you use the same technology to draw them. They're called histograms. The idea is that you're counting, you set up an experiment, and you're measuring one particular quantity over and over and over again, okay? But that quantity can change. So sometimes the number comes out to be 90, sometimes the number comes out to be 125. Is those of you who knows about gambling, like if you roll a dice, right? If you roll the dice enough times, if it's a fair dice, the chance of it being 1 is going to be 1/6, 2 is going to be 1/6, 3 is going to be 1/6, and so on like that, right? That's kind of a boring case. If you throw 2 dice at the same time, do you know what's the most likely number to come up? Anyone? 7, yeah. Okay, because that has the most combinations that for it to come up. So if we have 2 dice and we just keep throwing it, you're going to see a peak, like kind of seeing a peak at 90 here. You're going to see a peak around 7, and then it'll distribute it out. Okay, and so that's the idea of a counting experiment, is basically figuring that out. So as you can tell, right, what you record on the data is not what you're plotting here, right? I'm not plotting 1, 2, 3, 4, 5, 6, 7 all the time, right, on the dice roll. I'm plotting how many times does the dice comes up 1, how many times does it come up 2, 3, and 4 like that, okay? And these are called counting experiments, and these are very common in STEM. That's why I wanted to make sure we get a good handle on it, okay? As usual, the screen kind of sucks because um, it's a projector, but it looks good up here, but then it looks bad. Oh, now it looks good actually all over. Okay, and these are called counting experiments, okay? So the example I show is actually a plot that costs about $10 billion to make. So this is the discovery of the Higgs boson in 2012. And this experiment costs about $10 billion from all over the world to build. I think the US probably contributed something on the order of $1 billion to this. And this is an experiment known as ATLAS, where they basically measure what's known as the invariant mass. So basically, when they smash things together, stuff comes out, okay? And they just calculated how much mass was generated inside that event before everything exploded, okay? And they're able to calculate this, and a lot of times it comes out to be 90 times the mass of a proton. This unit GeV is just equate that to like AMU, atomic mass units. Okay, so something that's 90 times the mass of a proton comes out. Okay, you don't have to know what that is. It's not that important. But then something else comes out a little bit, but it's less than 90. That comes out about 125. And this is actually what's known as the Higgs boson. And it basically took physicists and engineers and chemists and probably some social scientists also about 20 years to build an experiment that can actually measure this and prove that this particle actually exists. Okay, and this experiment is still currently running, and measuring this 125 GeV times the 125 AMU mass thing over and over again, just to make sure that it is behaving as we expected in the physics model called the standard model. Okay. All right. As I mentioned, right. So when you do a counting experiment, what you're doing is you're counting how often the measurement comes out, right? The dice roll, right? Okay. If you throw 2 dice together out at the same time, okay, the most likely number you're going to get is 7. The 2 less will be 8 and 9, and then, damn it, 6 and 10, right? The least likely number is actually 2, because you cannot get 1 or 0 because you're throwing 2 dice out, and 12, right? Those are the least likely one, because there's only one combination of dice that allows you to do that, okay? So what we're going to do is we're going to kind of simulate some data in Python so that we can, kind of emulate what this plot does without, having to dig through, spend $10 billion to make that data itself. But that's real, but this is just a little toy thing that we're going to play with, okay? So in Python, there's a, actually, it's a library called NumPy that we've been using, right? NumPy, numerical Python. There's a random functionality in it where it allows you to basically create random numbers. And by random, there are specific types of random we want to use, okay? The first one is going to be an exponential, okay? So basically, exponential decay curve. That's a useful curve to have, okay? And the way you make this is just NumPy, random, exponential, and then of course it's a function, so you have to tell it, give it like the ingredients, right? The things I talked about last time. If you want to make a smoothie, you have to put the ingredients into the blender. So this is the blender, okay? The ingredient is the number 50, which tells you basically how long the exponential decay tail is. The bigger the number, the longer that tail, okay? And size equals to 10,000, so I wanted to make 10,000 events, okay? All right. The other one I'm making, okay, even though it's a Gaussian, computer scientists call this a normal function. It is, okay. Normal to me sounds weird, but okay. But it's called normal function. It's actually a Gaussian, the ones we played with last time, where it's basically just distributed. Let me draw one, right? Draw these two functions out so you remind people what the shape looks like, okay? So the exponential, right? It's going to look like something like this. Sometimes it kind of looks like 1 over x, but it's not really 1 over x, right? Okay. And then the Gaussian, right, it's going to be kind of this kind of peak thing, right, where this is like x bar, the average x, and then you have a width to this, minus sigma, plus sigma, right? So those are the two populations we're generating, okay? But, like, let's say if we plot these in, matplotlib, right? It just looks like this, right? It looks nothing like this, right? So I'm doing something wrong, right? So, because what I'm plotting is basically, oh, well, for every data point I generated, right? I just put that value as a function of x, function of x, function of x, and it just kind of collects like this, right? But there is a little bit of shape to this. You can see that mostly it collects on the low numbers, right? Which is interesting, right? Okay. So maybe we can think about an exponential. Why would a lot of the events, why would a lot of the dice roll, if you're sampling from an exponential, come out to be a very low number? Why do you think that is? Right? It seems to collect a lot down here. It's like, you're shaking a bin of cereal and then a lot of the small cereal falls to the bottom. I don't know. It's a good example of that. Do you guys see this shape where, like, oh, a lot of stuff seems to be on the bottom, not so much on the top, right? In fact, it only goes up to like 500. Yes, see? They're closer to, yeah, they look like they're closer together. In fact, a lot of the blue dots are actually overlaid on top of each other, right? I can even make the blue dot even smaller, right? Let's see. Let's see if I can make this smaller, right? Is this size? Equals to 0.01. I don't know, I think this might break it. Oh, I need to generate the data first. Okay. But think about why are there so many more dots on the bottom of that curve versus the top, right? Right, look at this. I'm plotting the exponential data mostly, okay? Right, this is the important connection. Why does this, I can connect that to the exponential? Why are there so many small numbers coming out, okay? So the way this random generator is doing, what it's doing is that, okay, it's gonna close the computer's gonna close its eye. I'll pick a number from here, put that on the vertical axis here. Pick another number here, put it on the vertical axis. Pick another number, put it on the vertical axis. The probability of it picking that number depends on how high this curve is. Okay, so which number will they pick the most if it's on this curve? Right, right. The small numbers, right? In fact, it's going to pick 0 most of the time, actually, right? Okay, so that's why a lot of the dots ended up on the bottom here, right? Okay, you can already understand this, okay? But now we're going to make a plot that's going to make it so it's much more obvious what we're doing, okay? And these are known as histograms, okay? So in order to make a histogram, you use the NumPy function called histogram, okay? Surprise, surprise, okay? And there's a couple of steps to this. And I know those of you who had other histogram experience before, there are shortcuts to making histograms. I want you guys to make it this way in this class. That way you can actually do the calculations yourself, okay? Okay, so in this little example here, right, I made a random exponential, right? Instead of 50, I just made it shorter, so 1.5. And I generated only 15, I rolled the dice only 15 times, okay? Just so we can see the numbers, okay? All right, and I printed out the example data, okay? Let's run this again. It'll change probably a little bit, okay? So the first number that this generator spit out is 1.3, 0.4, 0.75, 0.2, 0.74, 1.4, right? You know, just some numbers, okay? And these numbers are fairly small, most of them, right? They're not like 50 or 100 like that. The biggest number we got is which one? Maybe this one, 2.3, right? Okay, the biggest number we got is 2.3. Okay. There's a 6.5? Oh yeah, there's a 6.5 all the way out here. Okay, cool. All right, so this is going to be represented in your plot. Now, you guys are making the histograms in your head as I read these numbers to you. How often does this number come up? Okay, and that's what this histogram is showing you graphically. Okay, you can see a lot of numbers. In fact, 9 of the numbers are between 0 and 1. Okay, 3 of the numbers are between 1 and 2. And then two of those numbers will be between 1 and 2. And then, of course, there's this one outliers at 6, right? Bigger than 6, between 6 and 7. Okay? Let's make sure that we can connect these numbers together, okay? Because oftentimes, a lot of students, such as myself, when I first learned about histogram, did not understand how this actually works. Okay? I just knew, oh, I just type histogram in Python, it makes a histogram for me, and I don't need to understand what it does, right? Okay? So let's take the first number, right? So this 1.3, right, it's going to be between 1 and 2. So what the computer is actually doing is it's stacking Legos up for you, okay? All right, the next number is 0.4, so it's going to stack it over here, okay? 0.75, where should I draw the next box? Actually, I'll draw this one, okay? It's between 0 and 1, therefore it stacks to the next hill up here, okay? All right, 0.2, where should I draw the next Lego? Where should I put the next Lego block? These.
Dividing almost that. No.
Okay, tell me when to stop. Here?
That one.
Okay, okay, good. Okay. Well, I didn't make these bars long enough. It's actually supposed to go all the way out here, right? Yeah. Okay. Next one is 0.74. Okay. So if someone on the right-hand side, tell me when to stop. I'm going to stop moving my hand. I'm going to draw the Lego block here. Yeah. When to stop? Stop. Okay. All right. So there's 1, 2, 3, and now we have 4 events here, right? We rolled the dice 5 times so far. We got 4 times that's less than 1. Okay. And then 1.4. Okay. Someone in the back of the room, tell me when to stop moving and draw my box. Okay. All right. You're too late. Stop. Okay. So I draw the box here, right? Okay. All right, that's 1.4. I'm going to fill a little bit more of these out, okay? And then the next one will be up here, okay? What about this 6.5 number? Someone in the front of the room tell me when to stop and put my Lego down. Okay, good. All right, you guys are understanding this. This is good. This is a lot better than what I understood, even in graduate school. Okay? And then what happened is that it just read all these numbers, so it start filling it up, filling it up, filling it up, filling it up, right? And there'll be some couple of, there should be another number between 1 and 2 at least, right? Where is that number? Yeah, it's this last guy here actually, right? And there should be two numbers between 2 and 3, which is this one and this one. Yeah, great. So that's how a histogram gets made. Okay? All right. Simple enough? Right? Everybody is able to, you guys are gonna write a paragraph and describe how this actually works with a little bit of visual aid if you need it. Okay? So now you get to do this yourself. Okay? Turn on your computer, open your Jupyter notebook, make a new notebook for this assignment, Lecture 4 assignment. Okay? What I want you to do is generate 10,000 events and count them up, make the histogram manually by yourself with 10,000 events instead. You guys aren't yelling at me. That means you didn't understand what I just asked you to do.
10,000 events.
And then count. So do the same thing here, right? That's what I did here with 15 events, but do 10,000. Yeah, okay? Is that okay? For a professor to ask you to do?
Well, all we have to do is change the number then maybe.
Well, I want you to do it by hand, as I did with the marker. Okay, so I guess you guys don't want to do that. Okay, so generate these 10,000, have the computer make the histogram for you, okay? And to make the histogram, oh yeah, I covered this, right? For the computer to generate the histogram, right, you use this NumPy histogram functionality. You give it the sample data, right, whatever the data is, that list of, dice rows, okay? The other thing I want you guys to put in is the bin size. So bins equal to NumPy A range 0 to 10, comma 1. That's gonna be good for this histogram because, right, the numbers are from 0 to about 10, right? But down here, right, when the decay constant is already 50, you probably want to go a little bit further out. In fact, I tell you to do it from 0 to 200 instead. And the bin width should be 10. So you need to make a list of number from 0 to 200 where the interval is 10, okay? And the magic is this functionality up here, right? A range, okay? So just note that, okay? So after you make the histogram, okay, what it actually does, so pay a little bit of attention if you can, if you haven't seen this particular functionality before, okay? What it returns to you is basically the Y value, how high each of the bars are, okay? And it gives you the bin edges. It doesn't actually give you the bin center, okay? It gives you 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, okay? Okay, if there are, from 0 to 10, there are going to be 11 edges. Does that make sense? Right? But if you're making a plot, right, so this number is 9, this number is 3, this number is 2, 0, 0, 0, 0, 1, 0, 0, 0, right? There are 10 numbers you're plotting against each other. In order to convert the bin edges to the bin center, okay, I'm just going to give you guys the code because you can look this up on the internet if you need to anyway. It's just this little code where you just pass it all the element except for the last one, okay? And then all the element except for the first one, and then you divide by 2, okay? You can stare at this little one-liner, okay, and figure out why does it actually work to calculate the average bin edges. You're basically taking the two sides and then taking the average of those two numbers all the time, okay? And then when you plot this, now we're going to plot bar graphs instead, okay? Remember, these are called bar graphs in math and non-physics, but we're actually plotting histograms, okay? The way you plot the bar graph is the same way you make a regular plot, but they come out as bars instead, okay? So you want the horizontal to be your bin centers, and then the vertical to be the height of the histogram. And you want the width, in this case, in your case, it's not going to be 1. You're going to want this to be 10, right? because each of your bin width is going to be 10. Okay, so here's the instruction. Okay, to at least when you get the first 2 steps, you'll get a histogram. The other thing I want you guys to do is actually put the y on the log scale. Okay, that's their first cell. In the second cell, I'm going to have you generate that 100 Gaussian events. Okay, where it is distributed around 125 with a width or sigma parameter of 5. Do the same thing, make a histogram out of that, and make the y scale log scale also. Okay. So let's do that. I'm gonna pause the. So hopefully what you guys see are this, right? So you have this when you put it on a log scale. Okay. So an exponential function, right? This is something that's very useful to know, right? Is e to the some amplitude e to the minus x over maybe tau or something like that, right? Whatever it is, right? Let's say this is my y as a function of x, right? If you plot it on a log scale, it looks like kind of a straight staircase, right? And that's because, right, if you take log of this side and log of this side, in this case we're taking the natural log actually, right? So log, let's just do it in math language, natural log, right, of y, right? What happened is that this is actually going to be natural log of a times natural log of exponential minus x over tau. And how are natural log and exponential related to each other? Well, yeah, they're inverse function of each other. Just like multiplication and division, when you multiply by something and then you divide by something, you did nothing, right? So these are just inverse function of each other. So what happened is that this will just equal to natural log of a times negative x over tau, and this is basically right, this is the variable and this is the slope, right? This is just a straight line, and that's why whenever you're thinking, oh, is this an exponential function, right? Take the natural log of it. If it's a straight line, then it is, right? If it's not, then it's not, right? So that's very useful. I also put labels and titles on all these. So what I'm going to call this is going to be histogram of simulated exponential background. We're going to call this the background, and we're going to see why this is called background. And then on the horizontal axis, I want you guys to call this the invariant mass in GeV. Don't worry about it. If you don't know what GeV is, just equate this to atomic mass unit. Okay. And on the vertical axis is the number of events, right? Okay. The vertical axis is not the value you get from dice roll, right? It's how many times you get that dice roll. Okay. So the vertical axis on the histogram is always going to be the number of events. Sometimes people, what they do is they call it a normalized histogram, where they basically normalize the area of this graph to be 1. So this will become a percentage instead, right? Okay. So whenever you see normalized histogram, that's what that means. Is they just normalize it to 1. So this is just like probabilities instead. Okay. So the Gaussian looks like this, right? So you have a strong peak at 125 instead. Okay. But the color, so you have this exponential background, and then this is what we're going to call the signal. Okay. Right. What I'm going to do is I'm going to plot these two together, and this is known as a stacked histogram. Okay. Right. So notice that. Right. I'm just going to show you what it looks like. You have the exponential blue, and I basically put the red Lego blocks on top of the blue. Okay. It's stacked on top of each other. Okay. The syntax to do this, okay, you make your first histogram, right? Basically, you have your exponential, you do your little histogram calculations, and then you put your histogram on the bar graph, okay? And then you do the same thing with the Gaussian, okay? And you do your histogram analysis once again with your Gaussian, but this time you do not have to recompute the bin centers anymore, because the histogram for the Gaussian and the histogram for the exponential, they have the same bin centers, right? because you made it out of the same bins here, right? Right. So, in fact, what I did is I just used the exponentials bin edges. Because you want the histogram to share the same binning, because otherwise, if they don't have the same bin size, then you're not comparing apples to the same size apples, right? So that's gonna mess you up. Okay. All right. In fact, what you can do is just put a little underscore here. So so instead of taking the exponential bin edge back, I just put a little underscore here as just a way to just dump this stuff out so I don't use it. Okay, it's just a trash bin. Okay. All right. And then when you want to stack this on top of it, the red on top of it, okay, you add one additional argument called bottom. Bottom equals to the other histogram, right? Okay. So you're basically putting one histogram on top of another, okay, and you stack them on top of it, and then the one on the bottom is called bottom, right? Just to differentiate the two, I made the Gaussian red instead of blue, okay? So anyone want to tell me why this doesn't, this red shade doesn't look like this at all, right? I thought it's supposed to look like this. How come it doesn't look like that? It looks almost like flat. Anyone wants to venture a guess why it doesn't look as what we generated? Something went wrong here? Did I do something wrong? Seth, all the way back?
Taking the events from that histogram and just setting them on top of the other one. So if you look, they still have the same relative sizes to each other, but they've all been basically placed on top of each other.
Right. They all have same relative size. They actually have the same size. Don't get tricked, okay? It's very important for you when you read a graph on a log scale, okay? The width down here is not equal. These two bins does not have the same number of events in it, right? This goes from about, 105 to about 108 maybe. This bin size goes from 110 to 120. They're very different, okay? So be a little careful when you're reading log scale plots because, yeah, and also the relative size, so like the basically how high this is compared to this, right? Because you're stacking them on top of each other, right? This bin is actually the biggest. The next bigger bin is actually this one. The smallest one is actually this one, right? Because it's actually lower, right, on the log scale also, okay? So be really careful about this. Okay, so now we're gonna think about as well, I have this red stuff, right, on top of my background. So the red stuff I'm gonna call signal, the blue stuff I'm gonna call background, because I wanna see if I can detect, this red stuff, which is actually a mass of a particle at 125 GeV, okay? So this is where we go into a little bit of statistics where we're thinking about, okay, if we want to figure that out, we want to calculate this thing called the signal to noise ratio and the significance of this, and this is where we get into a little bit of statistics, okay? So what we can do is actually we can just literally print out the values here, right? Whatever this number is, this y number is. If you did that, okay, you're going to get these numbers, okay? What I did is I basically combined these three arrays together, okay, using this thing called stack. Don't mess up array stack with stack histogram. Okay, to stack histogram, you use the bottom function. To combine stack arrays on top of each other, you use a numpy dot stack. Okay, so there's just a lot of syntax that while you do it once, you write it down, and then and then in the future you look it up. Okay, basically that's how you do this. Okay, if you print out these numbers, so the first column here are the centers of the histogram, right? Expo bin centers, right? That's the first column here, okay? The second column list of numbers here are the exponential histogram. So that's the exponential background we're seeing here, okay? It starts out very high, like almost 2,000, and then it gets smaller and smaller and smaller and smaller, and it just decays exponentially until the end here, okay? The Gaussian is the third column, okay? It has nothing, 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 until it gets to 115 where you got 20, and then 125 you get 64, you got 135 you got 16, you get nothing. Okay, so hopefully these numbers that I printed out make sense, right? So there you got some numbers here, a lot of numbers here, a lot of numbers here, and that's representing the third column here, right? Okay, this middle column is basically the height of this histogram at every on the blue. Okay, it's just decaying exponentially. Okay, the first column is the numbers on the horizontal. Okay, you don't have to do this. It's just so that I can compare these numbers, right? Okay, so let's say, I mean, I want to figure out, oh, is there something special going on at 125, right? The background, right, the noise is 174. The signal I'm getting is 64, right? So now can I say, oh, definitely I discover something at 125 GeV or not, okay? Is there a way for you to state that so that is quantitative, right? You can't just say, oh, well, there's more stuff there than I expected from background, therefore, you know, I should win a Nobel Prize, right? You can't say that. Okay, so how do we definitively, all right, state that you observe a signal or not, okay? And this is where we do a signal to noise calculation. And the signal to noise calculation is fairly simple, okay? SNR, right, is the probability, okay, or also known as the power of the signal divided by the power or the probability of the noise, okay? So these are probabilities. They're not the number of signal, but the probability of the signal is proportional to the number of signal events, okay? In this case, since we're looking for the third column here, the signal is actually 64 in that particular bit, okay? That's easy to do, but the probability of that noise being there is not 174, okay? Okay? Because we are expecting, we kind of are expecting 174 background events. The things that the power of the noise is basically how much that noise can fluctuate up and down to contaminate our signal, okay? Okay, all right, so how do we quantify how much noise comes from this 174 events? Okay, in order to do this, we go to the river and we ask the fishes, okay? This is where we get into Poisson statistics. Okay, so statistics on fish. So you go out and you go to the rivers and you talk to all the fish and you collect information from them, right? That's how we do Poisson statistics. No? Maybe. Okay. So Poisson is actually just some dude, probably some French guy. Poisson means fish in French. And he came up with this distribution called the Poisson distribution, where it allows you to count events from a counting experiment and figure out, convert the number of events you get into probability of you seeing that particular number, okay, given some average, okay? And this is some crazy equation, okay? P Poisson is a function of R. So, you know, if you don't like R, just replace this with X, right? This is the horizontal we're talking about, okay? And this function is mu. What the hell is mu? Mu is basically the expected number of events. So in our case, it's going to be 174, okay? Okay, 174 to the R power, okay? Okay, and then exponential of negative 174 divided by R factorial, okay? All right, don't worry about how this function gets calculated, okay? So let's just look at what it looks like, okay? All right, so if mu is 0.5, let's say you're on average, you're expecting only half an event, okay? The distribution, right, for the chance for the number of events you observe to be between 0 and 1 is going to be about 60%. Okay, so sorry about the bad pictures here. Maybe that, yeah, so now you can see it, okay, 0.6, okay, around 0.6, okay? The chance for you to actually see, okay, if the average number that from your dice roll is coming out to be 0.5, not that you can't do that, right? Right, but for the number to come out to be between 0 and 2 is actually 30%. Okay, even though the average is 0.5, there is some chance for it to be bigger than 1. right? Okay, and that's only 30%. For the number between 2 and 3 is actually about 10%. Actually, anything greater than 2 is actually about 10% of the time you're going to get a number that's bigger than 2. Okay, right? So this looks like this. Okay, this is known as a Poisson distribution, not exponential, not, x1 minus x. Okay, it's this crazy function, right? Okay, all right. If you increase the average number, let's just skip 1 because it's very similar to 0.5. Okay, if the average number that you're expecting, meaning the number of events you're observing, is about 4 instead, okay, right? So meaning up here, when we're looking at this, right? Let's look for, well, we don't have one like this. The number of background events, instead of saying it's 0.5, the average background is 4 instead, okay? Okay. How much would that fluctuate? Okay. This is how this will fluctuate. Okay. So it's going to center right around, between at 4, right? So the chance of it being slightly less than 4 or slightly bigger than 4 is the highest, right? So hopefully that makes sense, right? Oh wow, if your average number is 4, right? Most likely you're going to get 4, right? But that only makes up for about 40% of the distribution. Okay. Right? You roll the dice, right? It comes out 4, only 40%, 40% of the time, 4 out of 10 times. Okay? The other times it fluctuates further away from 4, right? And it kind of grows down like this. But what's interesting is that since when you roll a dice, you cannot get a number that's less than 0, right? You cannot count, you go out and count fish in the river, you cannot count negative fish, right? There's no way for you to count negative fish, right? Right? So therefore, it's not a symmetric distribution, right? Because this number can go all the way out to like 18, right? Right? If this distribution was the same, this number will go all the way out to negative 14, right? Right? But what's happening is that the left-hand side is basically kind of squished up against this 0 because you cannot count negative fish, but you can count positive 18 fish, so therefore it's not a symmetric distribution. But as you get bigger and bigger average number, let's say the average number of fish you find is 10, it gets more and more symmetric. Okay? Okay. Okay. All right. So yeah, if you want to look at this lecture from air propagation and Poisson statistics, there's one that's from Washington University that you can look through. Okay. So as I mentioned, mu is the mean, basically the average number of fish you see. Okay. P sub r is the probability of you finding that many fish on your next measurement. Okay. Okay. There's also one more parameter. Right. Is that it? Yeah. Okay. So yeah. So this distribution. So instead of looking at the graph, what we can do is actually look at a table of Poisson distribution, if you want to. Okay. So if your average is 0.5. For you to find, if the average number of fish you get is half, 0.5, or else known as 0.5, the chances are 60% of the time you go out and fish, you get 0 to 0.99999 fish. Okay. Okay. 27% of the time you're going to get 1 to 2 fish. Okay. And then, 30%. I read the wrong column. Okay. 30% of the time you get 1 fish, okay? And then, 7% of the time you're going to get between 2 and 3 fish, and so on like that. This is how you read out these. This is how that graph was made, right? Just putting bars on the y here, okay? Yeah. All right. Okay, so how do we calculate this when we're dealing with our counting experiment, okay? So you can actually numerically compute this without having to look up this table. Pretty close, not exact, okay? Okay. What you can do is you can calculate this using this little equation down here, where the uncertainty that we talked about last time, right, is actually not symmetric. Remember that that Poisson statistic is not symmetric because you cannot count negative fish, right? The positive with basically how broad the right-hand side is, you can calculate with just 0.5 plus square root. This is a big square root over all the whole thing. If I can see that. Okay, small, big. Okay, well, you can see it on the bottom one. There's a line all the way across here, okay? Basically, the square root of the number of average fish you're getting plus 0.5, plus 0.25, the whole thing square rooted, okay? If you want the left-hand side, how often you will get the 68% of the fish, you get this sigma minus. The only difference is that it's a negative sign in front of them, okay? You get a pretty good distribution from this. The goal is that you want to define the sigma parameters so it encloses about 68% of your distribution, okay? So if you go up here, right, where the picture is, right, if you go around this big, right, you want, this is about 68% of it, okay? And this is just what's known as a standard deviation, meaning it's just something that we pick in order to make it standardized. And we're going to see why this 68% is useful, because that's going to be that's actually going to be a parameter inside the normal, the Gaussian distribution instead, okay? But, right, the goal is to get to 68%. If you use this little method, the sigma plus sigma minus method down here, okay? If n is equal to 0, you get 63%. Okay, you're 5% off, okay? But if your n is actually equal to 1, you're 0.1% off only, okay? Right, and then you basically get almost the right number by just using this simple calculation here, okay? Sigma plus is equal to 0.5 square plus the square root of n plus 0.25, okay? Right, and then the negative side, which is going to be the left-hand side, the lower end, is the minus sign version of it instead, okay? Okay, this rule, right, simplifies greatly if n goes to infinity, right? So if you actually just take the limit of this function, right, sigma plus is a function of n, right? Take that as it goes to infinity, right? The only thing that that determines it is, right, it's going to be square root of infinity plus 0.25. Do you actually care about 0.25 when you're at infinity, right? So this is basically square root of n. Sorry, square root of n. Okay, square root of n, which is basic, but n is infinity, so it's basically square root of infinity. It's still infinity. You add a little bit to it, you don't care about that. So basically, what happened is that as n goes to infinity, okay, the sigma basically just becomes square root of n, okay? And that's because, another reason, not just to make take the limit stuff, what happened is that as the average number of fish you're catching increases, right, the Poisson distribution basically become a Gaussian distribution. They get closer and closer and closer to each other. You can see that for average the number of fish equals to 10, it's still slightly off, but the two are pretty close to each other already, okay? All right. The Gaussian distribution, hopefully we already saw this, right, is defined as this, 1 over square root of 2 sigma square, e to, you know, r minus mu, where mu, remember mu, I'm using the same nomenclature as that Washington website, right? It's the average, right? It's the mean, this average number here, right? Which is, in this case, is 10, okay? And when you plot the Gaussian distribution, what happened is that when your sigma, when you go out to 1 sigma, meaning 1 times this, whatever this number happens to be, you know, it could be 0.5, it could be 10, or whatever it is, right? Right? When you go out 1 sigma in both direction, you get 68.2% of the probabilities back, okay? And that's where that 68% comes from, okay? Right? If you go out further, right, you add another 13.6% to each side, you end up with about 95, okay? Right? So in a counting experiment, right, if there were 174 events, okay, and you want to calculate how much that number fluctuates from 174, all you have to do is just take the square root of it, okay? Okay. So in this case, okay, since our signal was proportional to 64, right? Sorry, our signal is 64, but the probability of the signal is 64. Okay, the probability of the noise is actually proportional to sigma, and sigma is just square root of n. In this case, n is 174. Square root of 174 is actually about 13, okay? And if you take 64 divided by 13, you get a signal noise of about 4.8. Make sense? Okay. And 4.8 is a pretty decent number, okay? And scientists will call this 4.85 sigma from the noise, okay? Okay, how good is this? Okay, what we want to do is follow what's known as the 68, 95, 99.7 rule. You can see it on the Wikipedia. You go to all these symbols here. Okay, so if you are 1 sigma away from your noise, okay, you have a 68% of it being being able to be certain that you actually saw something real. Okay. If you're 2 sigma away, it goes up to 95, because you can see that in this little distribution here, right? The further away from the center you are, the less chance that it is just random noise making that making those data for you. Okay. All right. And then if you keep going, I'm not going to go through the other ones. Okay. But for at least in particle physics, in order for you to make a discovery, you have to make a 5 sigma calculations, okay? And so, and this is like a 3 in like a million chance of it just being random, okay? So if you're building a $10 billion experiment, okay, and you give the public an answer, okay, you better be pretty sure, right? Because otherwise, they're not going to build many more of these even now, okay? All right, so what we calculated was that basically the signal to noise was 4.8, and in this case, it's actually not enough for a discovery still, okay, because it's slightly under 5 still, okay, and that's what this will look like, right? All right, do I have more to talk? Okay, yeah, I have one more little box, and then we can do a little try yourself, and you can even take a break, okay? All right, so what we want to do next, okay, is basically have you guys calculate what the signal to noise will be like, okay? So in a new cell, right, first generate 5,000 background events with a decay constant of 50. Remember, the background is the exponential, okay? And then generate 50, okay, signal events, right? The signal events is the Gaussian that you guys did already, so you can just copy and paste all of the codes, okay? Make the stack histogram again with these values instead, okay? Okay. The sigma value should be 3, okay, instead of, I think the first time I have you do it is 5, so you have to tweak these things so I know that you know how to do it, okay? Make the stack histogram just like what I did up here, right? And then calculate the signal to noise, okay? And then repeat the same thing, okay? But double the number of background and signal events, okay? Instead of 550, you go to 10,100, okay? Which is what you did in the first place, okay? And then there's another one. I just want you guys to play around with this, okay? Instead of doubling the number of events, you double the width, okay? So you basically take what's from part 5, and you double the sigma parameters from 3 to 6, okay? And then just see how the signal to noise comes out, okay? So with that, I'm gonna. All right. So welcome back. So let's hopefully most of you guys got at least a couple of the at least one of the signal to noise ratio calculations done. So hopefully your plot kind of looks like this, where you have this blue exponential decay, and then instead of the red being at 125, the red is now at 95, right? Because you shifted the signal to be 95 GeV instead. Okay. All right. If you calculate the signal to noise for the first one, I just printed it out, which is about 4-ish. If you got around 4-ish, that should be correct. For the second one, where you're doubling the number of events on both the signal and the background, you should get something a little bit, maybe around 5. If you only double the signal, you'll probably get something around 8. If you only double the background, you'll probably get something like 2, okay? So make sure you double both, okay? And the idea is that if you double both the signal and the background, the way you do that is by just running the experiment longer, right? Because the background and the signal both will increase at the same rate, okay? All right, but since the background, right, the power or the probability of the background or probability of noise, that P noise, right, is actually square root of the number of events, where your signal is just a number of events. The more data you collect, right, the signal to noise ratio increases because one goes as n, the other one goes as square root of n, right? So you actually grow better statistics as you collect more data, okay? This last one here, where I have you double the width of the Gaussian instead, I think this from 3 to 6, right? Right? You should get a signal to noise that's a little bit smaller than the previous one. Does everybody, well, those of you who are able to get that, did you get that? Yeah. Okay. I'll let you explain why that's the case. Anyone wants to try to chime in? The same number of events, but now the Gaussian is broader. Why does it have the signal noise is weaker? Anyone? There's some discussion on the left side of the room. Well, right to you guys. But you're not gonna say tell the rest of us? Right. 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 So the Gaussian, right, the sigma parameter tells you how wide it is, right? This is what sigma is, right? Okay. If your sigma is bigger, with the same area under the graph, right, it has to be wider in order for that to happen, right? If this spreads out more and you're only picking, your signal is only coming from this one bin here, you're going to have less, right? Your signal gets weaker, right, if your data has more spread in it, all right? Does that make sense to everyone? Okay. All right. So what I want to cover next, and hopefully this will be the last kind of big thing I want to show you guys, right, is how to basically plot the uncertainties in your histograms also, okay? Just as a review, right, I'm just copying and pasting all the stuff here, right? If you want to have, if you're calculating the uncertainty on the number of noise events you have, if n is small, meaning like in this case less than 10, you should use this equation in order to calculate it, okay? It's an asymmetric uncertainty, right? The right-hand side of the Poisson distribution is not the same shape as the left-hand side, right? Where the Gaussian it is, okay? But if you have more than 10 events in the bin, you don't have to worry about it. You can just assume it's pretty Gaussian, and they're pretty close together anyway, okay? So whenever your bin, your whatever histogram you're making, that particular bin has fewer than 10 events, you're going to have to do this, because otherwise you're going to get the answer wrong, okay? If it has more than 10, then you're good enough, it's good enough to just do square root n, and that's about a 1% difference, okay? Okay? And all the experiments you do in here is, if you get to 1% of the answer, that's a miracle, actually. I actually don't believe that. Okay, so we know how to calculate the uncertainty in each of these histogram bins, okay? So let's look at an example where I'm going to, instead of an exponential, I'm going to make two Gaussians on top of each other, okay? Let's run this box, okay? Wait, did I do two Gaussians? No, I didn't do that. Okay, so let's ignore this two Gaussian thing. Okay, it's an exponential on top of a Gaussian once again. It's the same example you guys just did, I think, right? Where it's around 95, okay? Right? So this looks very well. It's like, oh, you know, if I ask you, oh, where's the signal? You just point to where the red is, right? It's like, okay. But in real data, right, the signal and the noise, your data is not color coded, right? Okay. In real life, you get this instead, okay? Because you know where the answer is, you kind of know where it is, right? Did I generate a 95 or a 125 in this case? 125. There's a little bump here, right? If you didn't know that a priori, you would not see this, right? Okay. So how do you picture this? Put that information, put those uncertainty on your histograms also. Okay. So this is where we're going to use these sigma calculations in order for us to add uncertainty to these bins, okay? Right? Overwrite, okay? The way you add it is using this functionality called error bar, okay? There are uncertainties, but of course, computer scientists don't care about the difference between errors and uncertainty, so that's why they call it error bars. Let me just show you what it looks like when you're making this, okay? So when you add the error bars to it, I want you guys to add basically black dots with black lines around it on both directions, okay? All right, so let's stare at like, where's the 125 one? Stare at this one, okay? All right, so you notice that the black dot is basically at the same height as the blue histogram, okay? There's no difference, okay? The width, how wide the horizontal bar goes, is the width of the bins, right? Okay, this up and down is this square root of n that I just calculated, okay? Basically, sigma up is the top edge of this little line. Sigma down is going to be the bottom of this line, okay? In this case, it's going to be symmetric, okay? Because we have so many events, right? So 100 something, right? Okay. The way you do this, okay, is first, of course, you're going to have to calculate what error plus and error minus is. Actually, I did it the fancier way. Never mind. I did it with the asymmetric error, right? Okay. So a lot of times to be safe, I think this is the reason why I did it, is because this histogram just keeps going, right? You're going to end up with bins with very few events. Okay. So to be safe, you should just do the. I mean, it's 2 lines instead of 1 line, so so you can do that calculation. Okay. Where the error plus, right, is just coded in as 0.5 square root of whatever the histogram value is plus 0.25, the whole thing square rooted, right? Because that's what we want up here, right? Whatever the histogram value is, how high it is, you add that 0.25 to it, you square root the whole thing, you add half to it, okay? Similarly, right, error minus, hopefully it's the only one thing that should change is this minus sign, right? So you should see that. To put this into the error bar, put this into a plot, first thing you do is you make the bar plot first, and you overlay the error bars on top of it, okay? You do both, okay? And therefore, they can see both, okay? And the way you put that on there is you PLT error bar, okay? You put the center and the histogram, so this is your X, this is your Y, just like you do before. But now it has an additional argument, right? Error plus, error minus, okay? If you did a symmetric error, you can remove this bracket and just give it 1 set of errors. I gave it 2 set of errors because I had an asymmetric error, right? Okay. 5, this next argument here, tells you how far to go left or right. Basically how wide these bins are divided by 2, right? Each of the bins is 10 in width, right? So 5 times 2 gives you the 10, okay? That tells you how wide the stuff is, okay? You can give it an array of numbers instead, and you can have a variety of widths in these bars if you want, okay? Try not to do that because it's really hard to understand that, because if you have variation in your bin width, some people do it because sometimes what happens is that, oh, your last bin has so few events, you just widen it so that you captures more events. It's very confusing to look at. I have been in meetings that took like hours arguing whether or not to widen the last bin or not. Okay. Okay. Anyway, so just make that a constant 5 in this class at least. Make your life simple. But you do have the option to make variation. There's a lot of different options here. This is the what's the LS? Line size, I think. Okay. And then the marker I put on there is dots. You can put stars or circles on it if you want. Okay. This is the marker color. K means black, right? Marker size 7. So one thing to note is that you want to be able to see these kind of bars here. If I make the marker size too big, then it covers up the bars, right? You don't want that. So you want to make it small enough so you can see it as a circle, but small enough so that you're not covering up the bars. The stuff that's up here, where it's covering up the vertical bars, is okay because, well, this is just, no one cares about the noise up here, right? Because your signal is actually down here, right? Okay, right. And then color, I think that's the line color is black, and then I'm going to label them error bars, even though I didn't draw the legend. So I guess I could draw the legend, plt.legend, right? Okay. Okay, now it has a legend. Anyway, by default, let me just show you what happens when you don't do this. I think, okay. By default, it kind of draws it like this. Don't know why, okay. There's some Python algorithm that determines, what's the best y-axis to show you. If you don't want your plot to look ugly like this, where, like basically you can't even see the error bars on your signal, right? You can zoom in using this PLT ylim. Ylim means the y limits, okay? So I want to go from, right, the reason I picked 40 to 2000 is that, well, my lowest point is around here, right? So that goes across here. So 10, 20, 30, 40, right? That's what my lower bar is, okay? The upper bar is the biggest number I have, is basically 1000, 2000, right? So it's less than 2000. That's why I picked 40 to 2000. That's how you can pick these y-lims, okay? So when the Python algorithm fails you to pick the right, heights, y-axis, you can do it yourself, right? Using the y-lim. And if you want to fix the horizontal, you can do the x-lim also, okay? You can change that. All right, so what's next? What am I looking at next? Oh, okay, it's fitting stuff. Okay, combining, okay. Any questions about this? Putting the error bars on your plot? Okay. All right. What we're going to do next is combine what we are doing today with what we did last Wednesday. Is basically fitting a curve through this and then drawing the curve, right? And that way, okay, even without calculating the signal and noise, now it's much more obvious just from looking at the picture where the signal is, right? Is it here? 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 Right. There's something going on here, right, compared to the red line, right? Okay. So by just having this picture, it also shows the reader that your data has some signal in it, and specifically at basically this one point here. All right, how do we do this? Okay. I'm going to go through this much quicker because we already did it Wednesday. Okay. What you do is you define a function that you want to fit to. In this case, we want to fit to an exponential. So you define an exponential that has two parameters, right? X is the independent parameter, right? That's the numbers you're feeding into the function. A is the amplitude of the exponential. Tau is the decay constant of the exponential, right? You define this. You set up some initial parameters for your fit that you know is correct. Well, you approximate, you don't know is correct. Okay, then you run this SciPy optimized curve fit thing, right? That has your exponential function, right? Your x and y values, the initial parameters, okay? And what I'm going to do is I'm going to run this with both. I'm going to run this like we did on Wednesday, and it produced the fit parameters to be basically, about 2000 and then 50, okay, around there. Okay. Now that we know how to calculate errors on our histogram, we can put in the errors after param 0. Okay, I'm going to give another parameter for you to pass to it. Okay. Unfortunately, curve fit cannot take a asymmetric error. It has to be symmetric. Okay. In that case, you always want the bigger one to be conservative. The bigger one's always going to be error plus. Remember, because it's 0.5 plus something, right? Instead of negative 0.5 plus something, right? Whatever that number is, the sigma plus is going to be the bigger number. So you give it error plus instead. So if you print out the fit parameters with errors, you can see that it is slightly different. Okay, it's like 5% difference maybe. Okay, so it is important for you to put in the uncertainty when you're doing the fit. Right? Otherwise, you're not accounting for the uncertainty in the fit. Right? And then in order to draw the fit on top of it, you basically just feed it into a function, right? And then you just, plot, right? Plot, okay? And then you have this nice straight red line, okay? Since it's an exponential on a log scale, this better be a straight line, right? Okay? And then obviously you can see where the signal is now, right? As opposed to previously, it's like, that little bump, is that like a real thing or not, right? Okay. All right, what am I doing next? Oh, okay. Okay. Stack, histogram. Okay, so what I'm going to do is also show you what's known as the covariant matrix. Okay. So whenever we're doing this optimized fit curve fit thing, right, it gives you two things back, right? The param fit, which is what I've been using right now. They'll also give you this param error back. So what the heck is that? Okay. So the param error, if you print it out, like down here, right after a right fit param covariant matrix, is actually a 2x2 matrix in this case because there's two parameters. Okay. The first number is about what, like 1400. The second number is like 0.7, and then there's also two numbers here that are like 22, 23. It's like, what the heck do these numbers mean? Okay. So this first number, right, 0, 0, matrix element 0, 0, is the square root, the square of the uncertainty on this number that would fit to. Element 1, 1 is the square of the uncertainty on fit parameter 1. Okay? 0, 0 corresponds to fit parameter 0. 1, 1 corresponds to fit parameter 1. These cross terms, the off-diagonal part of the matrix, okay, are what's known as correlations between the two. Okay? So it's a correlation of 23, big or small. Okay, hard to tell. The rule of thumb is that you basically, take the biggest number you have in your uncertainty, you compare that to here. Okay, so the biggest number is 1400. You compare that to 23. The 23 is much smaller than 1400, right? So you can say that these two parameters are not highly correlated. Okay, I'm not going to go through a whole statistic thing that's going to allows you to quantify the probability of the correlation, but you can just estimate, okay, if it's much bigger than the other, the two parameters are not correlated to each other. Okay, so if you want to print out the uncertainty without dealing with square roots and squares and like that, what you can do, right, you can just print out, instead of printing out the covariant matrix for the errors, you can print out the square root of it. Unfortunately, sometimes these number comes out negative, but you take the absolute value of it. So numpy.abs, right, your abs workout, makes it so that you can take the absolute value of your matrix. Because you don't want to square root negative numbers, right? Unless you're doing quantum mechanics. Okay, you end up doing square root negative numbers all the time, right? Okay. So when you square root this, now it's much easier to read. So the fit parameters we got was that, well, this fits up to, well, you know what the answer is, right? When we made this signal, when we made this background, what did we put as our how high this is, right? So you can even read this out, right? At 0, basically it goes to about almost 2,000. Okay, so this number should be about 2,000. Okay, and this is the decay constant we put in, right? We put in 50, right? Fit to 51.5, right? So that's pretty close. All right. Anyway, so the uncertainty on that is 40, right? This 2,000, you have an uncertainty of 40. Okay, and this 51 has an uncertainty of 0.9. Okay, so that's how you can put plus minus signs behind the stuff you fit to. Okay. All right. Sorry, I'm going to keep talking. Just one more thing I want to show you guys. Okay. So one thing that you may be asking. So, well, maybe you guys can think, okay, am I doing something wrong here by fitting this to an exponential completely? right? I'm fitting all the black dots to an exponential. Is there something that could be doing better? This gets you pretty close to the answer, but you could get closer very easily. Right, the signal is there, right? So what it's doing is actually this red line is being pulled up slightly by these black dots. That's not an exponential. This is a Gaussian right here, right? Huh. So how do we do that? Anyone can think of a solution before I showed it? Yeah. You can guess where your signal is, right? If you're expecting your signal to be 125, you just don't fit to those points, right? In fact, what I'll show you guys to do is basically, where is it? You do a fit. Oh, this is just a fancier printout. Let's not do that. Okay? What you're doing is you're basically selecting what's known as a background dominated region for your background fit, right? Because if you want to fit to your background, you pick the part of the histogram that is mostly background, okay? So, because the signal could be biasing the fit, right? And the signal in this case is very small. In the homework, you're going to see a signal that's much bigger. That's going to cause a problem if you don't do the background selection, okay? And it contaminates, yeah, as Austin said, it contaminates the fit. So therefore, what we can do is basically select what's known as a background dominated region to do the fit instead. So looking at this plot, right, where's the background dominated, right? We know the signal is here. Which part of the curve should I fit to instead? Yes, those stuff that are probably away from 125, right? You can even do stuff out here, but you know, there's only a few data point here, so stuff maybe between 0, 25, 70, 50, right? They're still all background. 75 is still all background, maybe 100, but you don't want to hit 125, right? You want to go up to 100, okay? So how can we do this? So this is done by just the stuff you guys already know how to do already by basically slicing and dicing your arrays, right? Because the fit is made, where's the fit made? Yeah? The fit is made, right, by your exponential function, and you're passing it your x value array and your y value array, right? You can make this whatever you want to. You don't have to pass it the whole thing, right? You give it a subset of the information, okay? So I think down here, plus, what I did is I basically made a little slice of the array. So the mixed histogram, right, is the whole thing, right? It's all the blue stuff, okay? And then what I did is I just picked out the array, right, from the 0th element to the 9th element, which gives me 10 numbers, right? So if we look at this, which number is it giving me? Okay, it's giving me this number, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, up to here, okay? So I got all the numbers up to 100 GeV, okay? Right? So I call that my, my background hist because that's the background dominated region, right? Instead of the mixed region. If I did this to the y value, I have to do the same thing to the x value, which is the bin centers, right? The x value is the bin centers, right? Because I'm plotting it as 5, 15, 25, 35, 45, 55, and so on like that, right? Okay. So I'm doing the same thing. So hopefully this makes sense from 0 to 10 again. So instead of passing it the mixed histogram, I'm passing it just the background dominated histogram, background dominated arrays, right? So let's see how this changed the fit. Okay. Okay. So with that, right, basically your amplitude went up a little bit, right? Right. And then this number is supposed to be 50. It went down a little bit because I think before it was like 51.5. Okay. So maybe if I rerun this, it'll be better. But anyway, so that's how you fit to basically a background dominated region so instead of including all the values here, you only included the stuff that you know where there's no signal. Okay? Okay. Last thing I'm going to show you is how to subtract this background, okay? Because making this plot, right? How do I know what shape this is? Is this even like, how do I know how real this is? So instead of just calculating this, the signal to noise ratio, what you can do is actually subtract out this background, because this red line is what you predict the background to be, right? So how do we do that? Okay. So what you do is you basically, not plot a lot of the stuff, okay? Okay. And then when you make the fit, right, you have this X fit, Y fit stuff, okay? And what you can do is just take your histogram and subtract it, right? Okay, so let me just be clear. So mix his, right? Those are these numbers. The height of these histograms is mix his, right? Okay. Go back down here, and I'm subtracting Y fit to it. Okay, where's Y fit on this plot? Plot it. What color is it? Is it blue? Is it black? Is it red? Is it white? It's red. It's the red curve here, right? Okay. So you're taking at every point, you're taking the height of the blue, subtract the height of the red, height of the blue, subtract them from red. So you can see in the background dominated region, they're pretty close together, right? You should end up pretty close to 0. Okay? But when you hit the signal region, that's when they're going to be different from each other, right? So you just subtract those two numbers, right? You're going to get close to what you expect the signal to be. Okay? So in fact, if you run this little subtraction code, right, and then plot, right, the background subtracted histogram, right, in your plot instead, okay, you're going to see something like this, okay? You're going to see some noise here because there's so many events here, this is just going to fluctuate up and down. And notice that I removed the log scale on this because it's easier to see. Okay, but here you can see that whatever this peak is, right, that has like 50 events, right, where is that? That lands right on top of 125, right? So you can just subtract your background model, right? The fit is actually your model, right, from your data, and you can figure out, oh, if I subtract it, I should only see the signal. You're going to see a bunch of fluctuations, right, because, right, there's so many events here. The fluctuation here is basically square root of n in this particular bin, right, which is like 2,000, right? Okay. But when you get to your signal, you should see a peak where you expect the signal to be. Okay. So that's all I got today.